Right, we've got a log graph modeling problem here. This is a sort of exponential modeling, really, but exp and log are so closely bound in with each other. They're kind of more or less the same thing. Um, and this is to do with a rare painting which is gathering value over time. Okay, let's have a look at the question. Um, the value of a rare painting V is modeled by the equation V equals PQ to the power of T, where P and Q are constants. T is the number of years since the value of the painting was first recorded on the 1st of January 1980. And the line L illustrates the linear relationship between T and log V, log 10, base 10V, since the 1st of January 1980. And the equation is this, and we've got to find the value of the constants in this exponential. So the basic idea here is we've gathered data over the regarding the value of this over time since since 1980, um, and um, and we want to fit it to this. We believe it's an exponential. It seems to be sort of accelerating away. So we believe it's an exponential. And the general form of this type of exponential growth is this. So V is connected to T. We've got these two unknown constants here in the general model, where P basically is the starting value, isn't it? So when T equals zero, then is going to be equal to P. So that's the starting value. And then Q is just some idea of scaling, sort of how quickly it grows. And to sort of imagine that, well, 2 to the power of X doesn't grow as quickly as 10 to the power of X, does it? If we look at the graphs of it. So this gives some idea of sort of how steeply it's rising. So um, uh, so that's what we could do. So we could actually plot these points out on this, and then try and fit this to those points. The problem with that, first of all, is that you would need a very tall piece of paper, because that's the nature of exponential curves. And the other thing is actually drawing a line to points which are kind of dotted around. I mean, there will be other factors which affect the price. So it's not going to sit, or all not all going to sit nicely on this this exponential curve anyway, even if we could identify it. So so what we would tend to do here is we would actually basically convert this into a log graph. So if we take the log, in this case, log base 10 of of this equation, we could use any base, but we tend to use log base 10 quite often for these, but say it could be base anything. Then what we're going to get is log base 10 of v equals, now we're using our log rules here, um, because the log of a product is the product is the sum of the logs, so that's log 10 base 10 of p plus log base 10 of q to the power of t. Then using another log rule, then basically log base q of t is going to be t times log base 10 of q. So kind of hope you can remember that. If not, then you'll have to consult another video on that. Right, so we see that if we rearrange that into like this, just switch the terms around basically, we can probably see that it compares very nicely to y equals mx plus c. This is your y, the vertical axis, which of course we've got over here. This is your gradient. This is your horizontal variable, and this is your intercept. All right. So now it's much more convenient to work with this, because now we're going to have a set of data points here. We'll have to take the kind of the log base 10 of the data points. But they're going to be sort of dotted around here like this. And it's going to be very much easier for us to draw a line of best fit or even calculate a line of best fit should we wish to use the relevant techniques or which we have on our calculator. But anyway, that we don't have to do that with this particular problem because the actual equation of this line is given to us in the question. There we go, up there. Now, in other forms of this question, we might be given a graph with scales on, and we have to work out the gradient and the intercept from that. But in this case, we're just given the equation, and so now you can see if we compare this that we're given with this general with it, well, this form which has come out of this, then we can see that our log base 10 of q is 0.05. That's the gradient. And that, of course, if we then exponentiate each side to base 10, that's going to give us, well, 10 to the power of log base 10 of q is q. And on the right-hand side, 10 to the power of 0.05. So that's going to give us q is equal to 1.122 to 4 significant figures. And similarly, the intercept here, which is 4.8, means that log base 10 of p is 4.8. And therefore p is 10 to the power of 4.8 equals 63,100. That's to 4 significant figures. That one there is a significant figure as well as the others. Okay, so that's what we have there for P and Q. So that is basically part A. With reference to the model, interpret P and Q. Oh, and incidentally, that therefore is the kind of the resolved model. That is this is the general form. This is the particular form of it with our constants found out. Resolved. So part B, well, I've sort of touched on this really. P is the initial value of the painting. That's the interpreting the value of the constant P, which 63,100 in 1980. And Q gives it's the degree of rate increase, really. So the bigger that number, the faster it increases. Right, okay, so that is more or less it. This is the sort of bonus for 2 at the end. Find the value of the painting as predicted by the model on the 1st of January 2010, giving your answer to the nearest £100,000. And yeah, so we're just using our model here, substituting t equals 30 in there, 2010 being 30 years after 1980. And so when we work that through, we get this figure out of the calculator. It's a rather surprising figure, in actual fact, even for me, and I've done quite a few of these, is that this painting is now worth an absolute fortune. And I think that's I think that is to the nearest £100,000 there. Yeah. So, yeah, quite worth quite a lot of money. So that is essentially it. So this is a relatively standard form of this question, but say there are variations, and you may be asked to actually find the value of the intercepts, and gradient yourself. They might give you 2 data points and say draw the line through there, and then from that you have to calculate the gradient and intercept. And there are a few other variations. We might actually be given some information purely in relation to this. We might be given the starting value, the initial value of the painting anyway, and not have to deduce it from the intercept. So, there's sort of various different flavors of these, but this is a sort of fairly typical vanilla kind of log graph question. So hopefully that has been useful, and I hope it's been interesting. And thanks for watching the video.